Multi-element linear arrays. Consider a set of antenna elements equally spaced by a distance d. It is called a uniform linear array. Suppose, for example, that the array corresponds to the antenna set located at the base station used to receive the signals emitted by the mobiles. Let's consider the transmission from a mobile located at an arbitrary point P. We would like to evaluate the signal power received at the base station array from that mobile. It is convenient to adopt a Cartesian coordinates system. If x1, x2, and xn represent the signal power received by elements 1, 2, and n, the array output may be represented by y, where w1, w2, wn represent specific weights that we could apply to the signals received by the respective elements. If the antenna elements are omnidirectional, the output y may be expressed by an array factor depending only on the frequency f and the wave's angle of arrival theta. For simplicity, consider that all weights hold the same value. If the array consists of just two elements, the array pattern is shown in the picture. If a third element is added, the radiation pattern shows a main lobe and two secondary ones with lower gain. With the fourth element, the main lobe gain increases even further. As more elements are added to the array, its gain becomes increasingly focused to a direction perpendicular to the line joining the array elements. This animation shows the array gain evolution as the number of elements grows from 2 to 32. This picture displays a subset of the configurations from the previous animation. Note that the maximum gain increases as additional elements are added to the array. Also note that main lobe widths decrease as well. The radiation pattern strongly depends on the distance between consecutive elements. Consider, for example, an array composed of 8 elements placed at 100th wavelength inter-element distance. When elements are such close to each other, the antenna array pattern is practically omnidirectional. The following animation shows the pattern evolution of this 8 elements array when the inter-element distance changes from 100th to half a wavelength. In summary, as the inter-elements distance increases, the maximum array gain does not change, but the main lobe width becomes narrower, therefore increasing the array directivity. Beam steering. One of the benefits of antenna arrays is the capability to focus the energy emitted to or received from a given direction. This property is known as beam steering. In this section, we will describe the corresponding mechanism, presenting some examples and discussing its limitations. Consider a uniform linear array and suppose, for example, that it is used for reception. Let's apply a specific delay to the signal received by each element. We suppose that this delay is a multiple of a certain value that we call delta t. Let's add the delay element's output, producing a combined signal that we call y. Consider the case where a plane wave arrives at the array. The wave direction forms an angle theta with the array normal. The wave arrives at element 1 with a delay d sine theta, measured with reference to the arrival time at element 0. This delay amounts to d sine theta over c and is called tau. In the same way, we can compute the delay of arrival corresponding to element 2. Its value is 2 tau. Let's initially concentrate our attention on elements 0 and 1 and call X0 and X1 the corresponding signals. In mobile communication systems, we deal with modulated sinusoidal waves, so X0 may be expressed as x of t multiplied by the cosine of omega 0 t. The signal produced at element 1 is affected by two delays, tau due to the angle of arrival theta and delta t corresponding to a delay that we arbitrarily apply to the signal received by this element. In a typical cellular system, the bandwidth of x of t is much smaller than the carrier frequency if 0, so the signal x of t will not change significantly after the delay t plus delta t. Quite frequently, these signals are expressed in complex form. It is implicitly assumed that we are only interested in the real part of the second member from the equation. The angle omega 0 tau is called psi, and omega 0 delta t is called small delta. Consider now the signal produced by element 2. It will be affected by 2 times the delay corresponding to element 1. Using the same bandwidth assumption mentioned in the previous slide, the expression corresponding to x2 of t may be simplified, resulting in the x2 of t expressions shown on the screen. In summary, this picture shows the signal contributions of the 0 branch, the 1 branch, the 2 branch, and the n-1 branch. Let's consider a practical example corresponding to an 8 elements uniform linear array. The interelement distance is half a wavelength. If no delay is applied, delta equal to 0, the array pattern is the same already presented. The main lobe points to 0 degrees azimuth. If we increase the delay, the pattern slips to the left, trailing the main lobe to this direction. In other words, a suitable delay can be used to change the pointing direction of the main lobe. If we increase the delay further on, the pattern continues to slip to the left. In conclusion, selecting the delay delta, we can steer the beam. Another way to visualize the steering capability of antenna arrays is representing the pattern in polar coordinates. This is a typical diagram found in the data sheets of commercial antennas. The following diagram corresponds to the same array described in the previous slide. We may see how the pattern can be steered by modifying the delay. In the following animation, we will see how to dynamically use this steering capability.